Hello everyone, welcome to the graduate student community at Gallery College of Engineering seminar series. Today we are excited to have Dr. Panchal, Professor and Associate Head of Undergraduate Programs in the School of Mechanical Engineering at Purdue University. Before we begin the talk, I would like to introduce the GSC team. First, let me introduce our leadership team for this semester, including our co-chairs, Rodney and Samuel, publicity team, Avinash and Supnil, treasurers, Anshu and I, and our support team, Zarin, Luis, Roshan, Rachel, Nurain, uh, Sidikur, Suramia, Vibha, and Hafiz, and for sure, our mentor, Professor Farooq Misri. If you are interested in learning more or joining the leadership team, please feel free to reach out to any of us. Every week, we have leadership meetings on Thursdays at 4:30 p.m. on Zoom. And if you would like to join, please email Rodney or Samuel, and they will provide the Zoom link. And the meeting times may change each semester based on the students' availability. As a quick reminder, if you have not already joined us, please become a member of the GSC on Engage because your membership helps us secure funding for seminars, other events, and of course, providing launches for these seminars. Also, please follow us on GSC LinkedIn page to stay updated on future seminars and events. For every week, we will publish a post on LinkedIn to announce our upcoming GSC webinars. We also encourage you to connect with us on Facebook and Instagram. We use these platforms to share seminar invitations, updates, and opportunities to stay connected with past and present members. Additionally, past seminar recordings are available on our YouTube channel. So if you ever miss a session or want to review a talk, you can easily find it in our YouTube channel. If you would like to join the GSC leadership team, you will gain access to the Bear Team Room, which is a perfect workspace with couches, whiteboards, a microwave, and a coffee machine, especially for a PhD student to study or collaborating with other students. Also, please fill out the seminar attendance form, which the link is shared with you or will be shared with you very soon in the chat. This helps us track participation and secure funding for future events and next seminars to provide the launches for this kind of webinars. Well, in each semester, we have a theme for our GSC seminar series. For this fall, our focus has been on research frontiers with generative AI, including issues, methods, and applications from academia and industry. And our speakers are addressing one or more of the following topics. First, how people can work with generative AI to create intellectual, economic, and social value and connect these domains. Second, research issues, methods, and applications that arise when people collaborate across research, industry, and community. And finally, ways of people to design generative AI initiatives that link academic inquiry, economic innovation, and social benefit in ethical and equitable ways. Our next webinar will be on November 19, featuring Dr. Dave from the Department of Psychology at the University of Oklahoma, and he will present a work psychology view of AI's potential, and we are looking forward your participation to the next webinar as well. And now I am pleased to introduce our speaker, Dr. Panchal, with today's talk on guiding large language models through the engineering design process. And now I will stop sharing my screen and pass it to Dr. Panchal. Welcome, Dr. Panchal.
Thank you. Okay. Can you see my slides?
Yes.
Okay, perfect. Thank you. Thank you so much, everyone, for having me as part of this group. And I'm really excited to share some of the work that one of my graduate students and I we have been working on for the past few months. This is focused more on using generative AI, specifically large language models, to help with the engineering design process. Now, I'm sure at this stage, all of you have used large language models, including ChatGPT and all of these other types of models that are available. And it's a very exciting time that we are able to do so much, in such a short period of time, that it is natural to see how we can use these tools to help with creating new products, creating new engineered artifacts, things that actually work. So along those lines, one of the phases of engineering design process that is important and challenging is the early stage design, which is coming up with new ideas out of the box ideas that can be used to solve some problems or that can be used to meet certain needs. Now, over the last, let's say, 60, 70 years, there has been a lot of work on developing methods for idea generation or methods for ideation. These includes things like brainstorming techniques, morphological analysis, design heuristics, and this is just a short list. If we list all of the methods, we can easily see there are like 30, 40 or so methods available. And all of these methods are primarily focused on trying to, one, expand the scope of types of solutions that are explored, types of design ideas that are explored. They're focused on trying to get people out of their narrow field of view, because if somebody is an expert in a certain field, they would most likely be biased towards solutions that they have seen in that field. So these methods are structured in a way that they take the people out of their comfort zone so that they can explore the design space much broadly. Some of these methods are also designed so that we can have a group of people who work together so that people can build on each other's ideas. So there are specific techniques where one person generates ideas, sends those ideas to the next person. That next person looks at those ideas and then adds value to those ideas and refines those ideas further or creates new ideas. There's a 6-3-5 method that follows the same approach. And the whole idea there being, again, if you have a team, instead of having n times the number of people in the room, we want to generate a lot more ideas than what the sum of individual team members would be. Okay. So now, with the availability of these large language models, the natural question that comes up is, these language models embed all the knowledge on the internet that is available. All the textual data has been somehow captured or synthesized within these large-scale neural networks. Can we try to come up with some ideation methods, or can we try to come up with systematic steps through which we can use these LLMs to get better ideas and more high quality ideas than what humans alone could do? And that's one theme that has been sort of popular within the engineering design community. You will see there's a lot of different papers that explore, even starting from GPT-2, trying to use these methods for idea generation. There have been techniques where people have used large language models along with some taxonomies within engineering design to generate engineering ideas. There have been people who have tried to compare what LLMs can do versus what students can do. Like, are LLMs better at generating new ideas, or are students better at generating new ideas? So this is human versus AI kind of a thing. And then there are some people who have also explored whether LLMs can actually replace the idea of crowdsourcing, where we go out and get ideas from hundreds and thousands of people, with the assumption that all of that knowledge is already in the network. Then why not just use that to generate these hundreds of thousands of different ideas? So, along those lines, there is this other field of work which talks about prompt engineering, which basically says that the way you prompt these LLMs will affect the output that you get. So there are different techniques that have been developed. There are techniques such as what is called chain of thoughts. So you ask the LLM a certain question, but then you ask the LLM to tell you how it went through the thought process to solve a certain problem. And that sometimes works better than just asking the question. Now, some of this chain of thought is now actually inbuilt into many of the recent LLMs. There are these reasoning models that automatically do this sequence of questioning internally, and we don't have to do that. There are techniques that people have proposed which include tree of thoughts, as in, you ask the LLM to generate a bunch of different ideas and then ask it to follow each idea direction and then break it down into a tree. And that way you're able to explore a large number of different possible ideas or solutions in that way. And then there are other more reasoning based techniques that are available that have been used for problem solving, for coding, for math problems, and so on. So the question is there a similar kind of a thing, or is there a new type of a process that we can follow in order to support engineering design, particularly in the early phase of design? So that is what drives this particular work that Bradley, my graduate student, is working on. So the central research question is, how can LLMs be used to support design ideation process? And the central hypothesis that we are using is, one, that LLMs can actually be used to increase the diversity of the kind of solutions that are generated. Okay, and I'll define diversity in a little bit, and I'll tell you exactly how we measure it. There are specific ways in which we can do that in design. But our approach is to say that, when you're generating ideas, what if you prompt the LLM with certain professional personas? And when I say professional personas, these could be things like a mechanical engineer, a doctor, a lawyer, a psychologist, and so on. Because the idea there is that if we tell the LLM that, you want to think about this problem from a lawyer's perspective, the LLM would go into that sort of knowledge base that is generally common within that particular field, and then use that knowledge base to generate new ideas that will be different than if it goes into just mechanical engineering domain or an aerospace or industrial engineering domain. And if we can prompt the LLM with a number of different personas and then take the union of all the ideas that are generated, then our hope is that we will get a much better diversity of design solutions that are generated for a given problem. Now, even within that, we can follow different prompting processes. We can do a sequential prompting, saying, okay, let's have the mechanical engineering persona generate ideas first. Whatever is generated, use that and then send that to a computer science persona. So then the computer science perspective will get embedded into the idea that is generated. Then take the updated solution, send it to the lawyer persona, and then some of the legal aspects of the solutions will be taken into account. So that's a sequential process. So that's one way to do it. The other way to do it is to do it parallelly, saying, let's say there are these 5 people with different expertise sitting on the table. Let each person generate their ideas, so each persona generate ideas, and then look at the union of that. And then the last one is more collective, which is in the same prompt, you give all of these different personas that the LLM should explore, and it is up to the LLM to figure out how it wants to combine all of these personas into a single thing. Okay, so that's sort of the approach that we are going to study first. We start with the problem, and then we create an LLM prompt with different personas, let's say 1 through n. For each persona, we generate a set of solutions or design concepts. Okay, and then we characterize each concept that is generated using a set of keywords. Okay, and then using those keywords, we try to assess whether the diversity of solutions is what is increasing or not. Okay, so we take a concept, which could be one way of solving the problem, and then we say, okay, how do you characterize that in terms of some of the keywords that we can use to now quantify how far apart these concepts are in some space. Okay, and we're going to talk about some of the details of each step. So when we try to do that, there are 2 main issues that come up. One is, when you generate a concept, how do you represent it, right? So, LLMs work with text, and, let's say it comes up with a solution that use lithium ion battery for something, right? Now, how do I compare that solution with, let's say, using a different type of a energy source, a human-powered energy source? Like I want to compare and I want to see how different are these. Is a lithium-ion battery, far away in some space than human-powered device, or is a different kind of a battery far away from that, right? So I want to measure the distance between these concepts. And for that, what we do is we typically map each of these words or phrases in some sort of a n-dimensional, high-dimensional space. Uh, and that approach is that step of mapping words into some quantitative n-dimensional space is called embedding. Okay. And this is a very common thing within machine learning and AI. And there are a lot of different kinds of embedding models that are available. And for this work, we used the OpenAI's latest text embedding 3 large model, which basically takes any text and then converts into a 3072 dimensional vector space. Okay. So if you look at the figure on the right, each point is some text, some phrase. And if two of these, and it's a 3000 dimensional space, so we have to project it and reduce the dimensionality to 2 dimensions so that we can visualize them. So if 2 points here are close to each other, which means that they are semantically similar. And we are basically saying that, okay, if the two things are semantically similar, they are very related ideas, so they're not as diverse. Whereas if you look at a point here versus a point somewhere on the complete opposite side, then there is a lot of distance between these two ideas. So the diversity of those ideas is higher, or the diversity of the collection of those ideas is higher. Okay. So the way we want to think about diversity is, if we are generating ideas that are far apart, then we have higher diversity. Whereas if we are generating ideas that are closer to each other in this space, then we have less diversity. Okay. Now here, you'll see some of these blue rectangles and some of these triangles. And these blue things are generated by one professional persona, like mechanical engineer. And then these other triangles are ideas that are generated by a psychologist persona. And that tells you that the psychologist persona ideas are closer to each other in this space than the blue dots, which are generated by the mechanical engineer persona. Okay, so that's how we are going to think about diversity, and that's how we're going to think about how we compare things. Okay. Mathematically, you can think about as mapping this idea into a single number by thinking about what is the volume that is encompassed by all of the points. Like, so if I take a convex hull around all of these points, what is the volume of that? And that is a measure of diversity of solutions. And our goal then is to maximize that diversity. So in order to test out some of these ideas, or in order to understand the effect of these interventions, we look at some design problems. And the way we pick these design problems is that they should be general enough that any different. So we don't want to have a truss design problem, which is minimizing weight and maximizing stiffness or whatever. Right? We want to have problems that are suitable for early stage design, where we can explore a broad design space. And here is a list of 7 problems that we picked, and these are from this paper from 2019 listed below. And these problems have been used a lot within the design literature. So those are problems. Then we try to identify what kind of personas do we look at. And we looked at these 5 personas. Mechanical engineering, because that's close to our expertise, so that makes sense. Then we looked at chemical engineering, computer science, biology, and psychology. So some of these are relatively close to each other. Mechanical, chemical may be closer to each other than computer science or biology and psychology. And then for each of these fields, we want to identify, okay, what are the different topics that, or what are the different keywords that characterize these domains? So if I think of a mechanical engineer, what do I think about? What are the things that a mechanical engineer would be familiar with? right? So instead of just writing down what a mechanical engineer is and what a mechanical engineer does, what we did was we look at the fundamental courses that are generally taught in an undergraduate mechanical engineering program. So we looked at things like thermodynamics, statics, dynamics, machine design, controls, and so on. So, and then we went to the textbooks of each of these courses that are widely used throughout the US. And then we looked at the table of contents of the things that are covered in each class. And that's how we came up with around 1,700 topics that sort of cover the field of mechanical engineering. Okay, so these would include things like first law of thermodynamics. This would include things like shaft design, stress analysis, fatigue, and so on. So these were the keywords that are part of that knowledge base. So this collection of topics is what we are calling the knowledge base within that field. Okay, and we are using that to assess how well the LLM is doing in terms of coming up with ideas from those related areas. Similarly, we did the same thing for computer science. These are the number of courses, these are the number of topics that were covered. So in all, we had around 4,400 topics that represented the points in this figure on the previous slide. Okay. So then we said, okay, let's pick design problems. And for each design problem, let's try out these different design processes. And here, when I say design processes, it's a sequence with which we are prompting the LLM. Right? These are the mechanical engineer goes first, then computer scientist goes first, and so on, to understand the effects of all of these things. Like, are these people all generating ideas parallelly or not? Right? So this step required a little bit of iteration. We had to try out different prompts to see, which of the prompts actually works best. And then after some iteration, we converged on a few prompts that I'm going to show you in a little bit. So here are some of the processes that we tried out. The first one was parallel prompting strategy. So I showed you this diagram earlier. So again, n personas, each prompted independently. Now, the way we did this prompting is not within the ChatGPT UI, because we didn't want the history from persona 1 to carry over to persona 2. So instead, we use the API. So each persona was a separate API call from OpenAI. So let's say the first one is mechanical engineer. We asked it to generate ideas for a particular design problem, and we asked it to limit to a certain number of concepts. From those concepts, for each concept, we asked the LLM to summarize that concept in terms of the professional terms or the knowledge items that I talked about in the previous slide. Okay, so for example, if you're talking about battery, what are the key things, key professional terms that characterize the battery, so that then we can put it in the same embedding space. The second strategy was sequential prompting strategy, where we ask persona 1 to generate concepts, and then we send those concepts to the next persona saying, hey, computer scientist, look, these are the things that the mechanical engineer came up with. Can you take this and either refine these ideas or generate new ideas based on what you see here, and so on. Okay, and then again, we collected the professional terms for each of these concepts, for each output. Okay. Here is the set of prompts that we used. Again, the first one is single professional persona, and it was something like this. I would like you to generate, and this thing in the curly brackets, we changed the number. We said, okay, 10 solutions or 5 solutions, depending on what we are looking at. Generate so many solutions for the given design problem. And this is where we wrote the entire string, which was the design problem, using the knowledge base of the profession, which was replaced by, let's say, computer scientist. And then we said, for each design concept, please provide a long paragraph of detailed technical description about how this design can be built and the specific professional concepts included in this particular design. So this is, okay, it comes up with some ideas, and then we wanted to explain what each solution does. Similarly, for multiple personas, we said, generate so many solutions using the combined knowledge base of this profession. And then if you look at updating design concepts, where we are also providing design solutions to the LLM. We are saying, okay, here are the 5 solutions generated by the previous person. Generate new designs or solutions for the same problem using the knowledge base of a different persona. And then we also had this prompt that summarized the design concepts in terms of these professional terms that allowed us to measure and evaluate the diversity. So here are some sample outputs that we got out of the first, this is the design problem, which is a lightweight exercise device that can be used while traveling. Okay, so that was the problem statement. And then if we use the mechanical engineer persona, it came up with these kinds of solutions, right? So travel fit portable resistance band. And then that concept was summarized in terms of topics related to material selection, because we are talking about resistance bands, so material properties are extremely important. So clearly that solution has to do something with material selection, with their properties, ergonomic design, structural analysis. So this is more the strength of the band, that it should not break under certain force applied. Then you can see some other things like compact cyclist folding exercise bikes. So since this is a folding bike, concepts related to kinematics become more important, and then dynamic loading becomes important.
Thank you so much.
But fatigue and so on. And then structural optimization becomes an important issue in this particular solution. So as you can see, for each of these solutions, it did come up with things that a mechanical engineer would associate with. Now, if the same problem was given with a psychologist persona, so here are some interesting things that came out. So when we talk about this first solution, portable balancing board, it talks about core stability, balance training. So it's now more focusing on the human being and what are the objectives of the human while using this device. For example, there are some other important stuff like mindfulness meditation was one of the solutions, which was not generated by the mechanical engineer persona. So again, this sort of gave some confidence that yes, it is indeed trying to come up with solutions that are somehow related to those personas that we gave out. And then here is one example of sequential prompting, where we start out by computer scientist, and the problem here is different. It's an innovative product to froth milk. So it came up with the AI-assisted frother as one of the solutions, an IoT-enabled smart frother, robotic arm frother. So some of the things that a computer scientist may relate with. When these solutions are given to a biologist, it added things like bio-inspired AI frother, right? Now, how good these ideas, at this stage, we don't care about that. In the ideation state, the idea is to generate as many solutions as you can, right? So some of these ideas may be poor or ridiculous at the first look. But from the ideation perspective, I think this is great. Biomechanical frother, sensory-driven, voice-controlled frother, which is an adaptation of this solution. And then we give it to a psychologist. Again, it added some keywords like cognitive, emotionally intelligent. I don't know what that means, but as you can see, it is trying to bring in some of those ideas here, and then further down to mechanical engineer, where it's adding more renewable energy into the solutions and somehow updating those solutions. Now, are these designs better? I don't know, right? But that's not really what we are trying to evaluate at this stage. So what we want to quantify is the actual impact. Can we come up with some quantitative way of saying that, yes, indeed, the diversity of solutions is increasing. Yes, indeed, we are generating solutions that are more aligned with the knowledge bases or not. So here are some hypotheses, and I'll show you some quantitative results for that. So the first one was looking at the alignment among different knowledge bases. So when we created those 4,400 items in the knowledge base, we wanted to first see, is there a difference between those knowledge bases or not? Is there so if I look at all the points for mechanical engineering and all the points for chemical engineering, are they the same thing, or is there a difference? Right. So that's the first thing we need to know, because if they're the same thing, then there is not much we can say about the solutions being generated, right? So here, the hypothesis was that the topics in the professional knowledge base are semantically more aligned with the topic within the same knowledge base. So if I take all the points within mechanical engineering and compare them with all the points within mechanical engineering, there is better alignment there than all the points mechanical and all the points chemical and so on. So these numbers, so the higher it is, the higher the alignment between, let's say, mechanical engineering topics and mechanical engineering topics. And these are color coded based on the strength of the number or the magnitude of the number. And as you can see, the diagonal entities are higher than the off diagonal entities, which shows that there is less overlap between mechanical engineering and, let's say, biology, and there is more overlap between ME and ME, and there is a large overlap between ME and chemical engineering, which sort of expected. So yes, so indeed these clusters of points are separate in that 3000 dimensional space. Then what we wanted to see was how much alignment is there between the concepts that are generated and the knowledge base in a given persona, right? And again, these are tables that show the rows are the personas that we used, and the columns are the knowledge bases that we are comparing those points against. Okay, so if you look at mechanical engineering persona generating some solutions, and then look at the overlap with mechanical engineering points, which is in the knowledge base, then there is a higher overlap. Right, so this strong the higher number has a more darker color. Okay, so the idea what this table shows is that if I use a mechanical engineering persona and if I compare that with the psychology knowledge base, there is less overlap. Okay, and there is more overlap between ME and ME, solutions generated and persona. So that does indicate that yes, we are able to direct the LLM towards generating solutions that is more aligned to those knowledge bases from these. So that is a good thing because that's sort of gives us some validation on the starting hypothesis that we had. Now, these are average numbers. Now, averages, can only tell part of the story, right? We also need to look at the whole distribution, and we want to see how much distribution is there among those distances between points, and that's what these diagrams show. So, if you look at this left diagram, what it shows is that I'm using the mechanical engineering knowledge base, which has a bunch of points, and then I'm measuring the distance between the solution points that are generated and each of the points in that knowledge base. Okay, so that's a set of different distance values. And if I plot those, the distribution or PDF of those distributions, this is how it looks. Okay, so the more to the right this distribution is, what it shows is that the similarity is higher between solutions generated and the knowledge base. Okay, so as you can see, what this shows is that there is actually a lot of spread, but still we can see that there is a higher overlap between mechanical and mechanical, and there's a lower overlap between mechanical and, let's say, one of these other fields. So again, visually this is sort of clear. This is, and in this right diagram we are showing biologist compared to biologist knowledge base. Okay. Another way to visualize this is by looking at the cumulative distribution functions. So these are the CDFs for the same plots, and this clearly shows that these curves stochastically dominate all these other curves right here, which again helps us in validating the hypothesis that yes, when we use the persona of a particular type, that persona will generate solutions that are more aligned with the knowledge base of that particular domain. Here is one other hypothesis that is related to the effect of parallel prompting using personas. So here what we're comparing is prompting without any personas. We just tell the LLM, okay, this is the problem, come up with solutions, right? And the other one is we are saying, okay, come up with solutions by considering all these 5 personas in parallel. Right, and here the y-axis is the diversity, which is the spread of the points in the space. And what we see is that yes, there is, in each case, whether you're using ChatGPT or Gemini 1.5 Flash or Llama 3.1, we do see a slight increase in the diversity of solutions if you're using parallel prompting. Then we go in a little bit deeper into the sequential prompting, and what we want to see is if I, start with the mechanical engineer and then go to a different persona, how much is the increase in diversity? Okay, so this table shows the percentage increase in diversity. So 0.97, which means around 1% increase in diversity if I first start with the mechanical engineer and then the second persona is chemical engineer. If I start with mechanical engineer and then go to the psychology persona, then the increase in diversity that I get in that two steps is 1.52. So clearly, some of these numbers are higher, like 2.19. If I start with chemical engineer and then go to psychology, then there's a greater increase in the diversity of solutions. So, so again, what this indicates is that maybe there is an optimal sequence in which we should be prompting. And can we identify that optimal sequence by saying that, okay, we should always start with the computer science person first and then go into the specific mechanical engineer? So we wanted to compare and see the effect of that sequencing. So what we did was we tried out, many different combinations of these personas, and then we tracked the diversity at different steps, right? In step 1, step 2, step 3, but we could not find much of a trend in how the diversity was changing. In fact, in some cases, the diversity was actually going down as we go from one step to the other step to the other step. So this was not very clear on whether there is an optimal sequential prompting or not. And what we found overall is, using the parallel strategy may be the best out of all of these different strategies that we have. This again, it shows some differences in terms of the distributions rather than just the average values. And again, here, since there is an intersection between these CDFs, it's hard to say whether there is dominance of any of these sequences or not. Okay, so that was the first study where we looked at just the ideation phase. Clearly, at that stage, when we are looking at solutions, we don't know how good the solutions are, and we want to be able to generate solutions for systems design problem, which are a little bit more complex, and we want to see whether the system solutions are workable or not. So that's what we are going to focus on in the rest of this presentation. So please feel free to stop me if you have any questions. We can have quick discussion. I think we have sufficient time. Okay. Let's say we want to solve a problem which is shown here. We want to design a robot gripper for picking up an aluminum Coke can. Okay, so that's the statement of the problem. Now, ideally, what I would like to do is for it, to go in, do the functional decomposition, come up with the requirements, do the functional decomposition for each function, come up with different solutions, compare the solutions, come up with different embodiments and, generate CAD models, send it to the 3D printers or order parts online and so on, right? So if you wanted to automate the whole process to go from here to a physical robot, which is programmed to do this particular task, there are a number of different steps. And interestingly, so when you give this to, let's say, ChatGPT 5, here's how it starts. It's a fun project. Here's a complete build-ready concept for a reliable gripper that can pick up a standard 12-ounce aluminum soda can and its variants without crushing them. So it automatically added this requirement that we don't want to crush the soda can. And it does go into identifying the key requirements. For example, it will say, okay, you're looking at a 12-ounce can, the diameter is approximately this much, the height is approximately this much, this is the wall thickness of 0.1 millimeters. All of this data is already in there. The mass, if it's empty, it's so much, if it's full, it's 0.37 kilograms. It adds a bunch of constraints to this. So this is just a small snippet of that. Then it goes into concept generation also. It comes up with a bunch of different concepts. Here are some examples. And then it does say, I'm going to pick this particular concept with parallel jaw gripper. And then I don't know whether it's actually doing the design or not, but it actually presents the results as if it is doing design, right? It says, okay, for the jaw, you should have a V-groove pad, 90-degree angle. This is the material that you should use with silicon rubber. For sensing and control, use this. Here's the pseudocode for that. And then at the end, it will also come up with a bill of materials. Okay, so this is all, to a non-engineer, who is not, to somebody who's not an expert in this domain, this may seem like, oh, this is really great, right? Everything looks really wonderful. But if you show this to any robotics person, they will easily identify 100 holes here, saying, "Oh, this doesn't make any sense. This doesn't go well with this other component that has been chosen. This kind of a switch will not work. These requirements are not okay, and so on." Right? As you can imagine, there are a lot of different issues that will come up. So basically, what LLM seems to be doing is that it's creating, a kind of a solution which look like, bringing these different, Frankenstein model where you're, taking one thing from here, one thing from here, one thing from here, and somehow just mashing it all together without really checking whether it makes sense to put these things together. What are the interfaces between different components and so on, right? And part of the reason for that is it lacks any underlying system representation. When we do systems engineering, we always start with some overall representation of the system, whether it's in the form of requirements, specifications list, or some sort of function structure, or in the form of some SysML diagram, and so on, right? So these large language models are not doing that, right? They don't have that hierarchical representation of the system in order to be able to do these kind of checks. Constraints and relationships between components are not maintained. Design iterations generally lose information. So, for example, there's always a limited context window. So as you keep asking questions, it will start forgetting what you initially told them. So if you want to follow the system switching process, you start with requirements. By the time that you are trying to actually design a specific component, it would have forgotten the requirements, right? Unless you are using such a large model which has a very large context memory, but then it's going to be too expensive to run everything. So there are a number of different groups that have been working in this. There are techniques such as what is called RAG, retrieval augmented generation, which basically takes the overall problem, looks at some existing sources like handbooks or some textbooks or some online sources, and then from there pull information and then use that information in the context window so that whatever is generated is informed by that context. Okay. For example, if you wanted to answer some questions about certain recent news, if you give the link to the news article, then it would use the information from that news article to give you the corresponding response. So it's retrieving information from some source, augmenting the response, the LLM response, using that information. So that's called RAG. So the way this whole approach works is that, let's say you're the client, you're sending a question and then you're expecting a response. Then there, and the LLM is sitting here. So instead of directly interacting with the LLM, you basically have some sort of an agent that goes out and pulls the right kind of information and then sends it to the LLM before generating the response. And there are many different versions of this RAG framework that you may have seen. Here is one version. This is from Microsoft. It's called GraphRag. It's a very powerful framework. So what it does is, if you give it a bunch of different documents, let's say design textbooks or something, then it will take each document, each large document, break it into text chunks, and then from those text chunks extract entities and relationships, and it will keep track of those entities and relationships and slowly build a graph out of that. So here is one example of a graph where these circles are entities and these arcs or arrows are relationships between those entities. Okay, so this is very much like the semantic web. Semantic web, where you have these different entities that represent the knowledge out there, and then using that graph, it is easier to do search, right? So it generates what is called a knowledge graph. So in the previous work, we didn't use a graph. We just used knowledge items, and they're all independent of each other. But here you can actually create relationships between different entities, which actually captures more knowledge than just words. And then when a user puts in a query, then it goes to the graph. From the graph, it identifies what parts of the graph are relevant to this particular query. And then it synthesizes the knowledge in those subgraphs by doing different community algorithms and so on, and then uses that knowledge to then give you an answer. Okay, so this is called graph RAG because you're using graph as the underlying representation of the information that is out there. There are a number of different ways in which these graphs can be built. These graphs could be built as just standard traditional neural network processing to identify these entities, and then creating these triplets, where these two are entities and then the relationship is in the middle. Similarly, there is this newer version of this which is called the light rag, and the way that it works is, it uses a cheaper LLM to do the initial part, and then when it's synthesizing knowledge, it uses a more expensive and higher end LLM to do that. Because if you're just looking at a paragraph of text, extracting entities does not require a very fancy large language model. You can do it with using a simple, maybe even local LLM. So again, this is just for background purposes. So the question that we want to ask is, can we use this approach to support engineering design or systems design? Okay, and our approach is as follows. There's a lot of design knowledge available in patents, right? So there are thousands and thousands of patents in all different fields. Um, all of these patents are available online through Google, US Patents, US Patents website, and if you go to Google Patents, you can easily download all of that, and you can write code to directly go and read any patent. Right. So this process of going and reading these patents can be automated easily nowadays. And then the question is, if I have a design problem, can I go out, look at the relevant patents that are out there, look at what kinds of designs they have used, and can I bring in those designs to come up with my system, come up my system design, come up with my different function structures or different embodiments for each function, and can I use that to come up with a design solution that has a higher likelihood of working, that is actually technically feasible and a valid sort of a design. So that's what we are trying to do in this part. Okay, so here is the process. So the first step is to select patents using the CPC codes, which is cooperative patent classification. So there is a hierarchical sort of coding system, and you can see a lot of these codes right here. For example, this particular patent is related to all of these different fields, right? So if you have a robotic gripper that has been applied for medical devices, you'll have codes related to robots, grippers, medical devices for specific types of surgery. That code will be there, and so on, right? So it's a way of finding these patents easily. So when we start with a design problem, can we use that to identify what kinds of patents should we be even looking at? So that's the first step. The second step is, now that we have identified these patents, can we extract knowledge from these patents about the designs that are used in the form of a knowledge graph, so that we can do graph rag kind of graph-driven queries. Now, if let's say we identify 100 patents, right? So each patent may result in a graph. And then if we take the union of those 100 graphs, then we may have a very large graph, right? We may not be able to put all of that information into the LLM as in the context window, because again, that will be too expensive or not even feasible. So how do we take that information and squeeze it or compress it in a way so that we still preserve all the relevant information and get rid of any duplicates or anything that is far away from them, that is not needed for that particular design problem, and then use that condensed knowledge graph as the context to the LLM, which then results in design. So that's the problem that we're working on right now. It's not complete. It's I'll show you where we are so far, and then there are a lot of other open issues still. Okay, so here is one specific examples. So we wanted to design a robotic gripper that could grip a Coke can. So we said, okay, again, there is a specific code that you can look at for manipulators, gripping heads, and other end effectors. So that's this code. And again, within that, there are like thousands of patents, right? Let's say we also look at two completely different fields of application where robotic manipulators have been applied. Okay. Let's say we pick one which is focused on harvesting, mowing, picking fruits. So those robot arms that are used to pick, let's say, apple and other fruits. Devices for shaking trees and shrubs, robotic devices for individually picking crops. So that's one field of application. So if you look for patterns that have both these codes, you will look at designs that have robotic arms or robotic manipulators with gripping heads, but applied to this application domain of picking fruits and vegetables. On the other hand, a completely different application could be handling semiconductor devices. So that's a very different applications, very different requirements. The scale is different. The kind of material that you're handling is different. The kind of care that you need is going to be different, and so on. So this particular code corresponds to semiconductor devices. Processes and operators adapted for manufacture or treatment of semiconductor or solid state devices for positioning, orientation, and so on. Right. So the idea is, if I generate a knowledge graph using this combination, and if I generate a knowledge graph using this combination, and if I use that as the context for the LLM, would I get very different kinds of designs or not? We wanted to see what kinds of designs are we able to achieve using that knowledge. So uh, so far we have not really focused on the first step, which is picking patterns. We just manually went and picked about 15 to 20 patterns in each of these classes, right? The second step is where we spend some time on, which is building a knowledge graph for each selected pattern. So we take the text from the patent, and then we want to extract a graph that represents design knowledge. Now, what is design knowledge? We tried out a bunch of things. We, use the LLM to say, okay, read this abstract, and from the abstract, tell us what is the design content. We didn't get much useful information. One, because an abstract has claims that are very high abstract claims, right? Because each patent wants to cover as broad a field as possible. So we couldn't really get much meaningful information just by looking at the abstract. So then we went on the description. In the description, it is a detailed, discussion of different parts of the solution. They'll talk about each component. This is what this component does. This is how this component interacts with the other components, and so on. So what we found, after some iteration with the prompts, what we found was that this combination seemed to work reasonably well. We first ask the LLM to extract all the components that are used in this design, because that's what the description is describing, right? So it's easy to do that. Then we ask, what is the role of that component in this overall design? So as a designer, we would think about function, right? So we're trying to say, okay, we start from the part that is there, and then we try to ask, okay, what is the function of this particular part, instead of going the other way around. Because we tried that. We said, okay, what are the functions, and then what are the parts? Then it didn't do very well. But given a part, it was able to extract the function better. And then we asked, what are the interfaces between different parts? And that's worked very well. So here are some examples. So these are the different kinds of components that were extracted. The power source, what is the function? It provides electrical power to the end effector actuators and the manipulator. A component was machine vision system. What's the function or responsibility of that? It's to identify and locate food positions in the 3D space. It's for handling variable lighting, occlusion, and clustering challenges. Okay, so this helped us extract, in automated way from a given patent document, this kind of design knowledge in the form of this graph. So if you look at the graph carefully, then this is a patent number. It has a component. Each component has some responsibility. So each component may have multiple responsibilities in the overall system. Now, the third step was to take all the individual graphs from each patent and then condense it into some sort of a smaller graph that we can put as input to the LLM. And this is where we used simple hierarchical clustering. We said, these are all the different terms that are there. Cluster these, and we can, since it's hierarchical clustering, we can specify the number of clusters that we wanted at which we prune the tree. And then depending on how big of a context window we want, we could provide more or less information that is from the graphs. So here are some examples. If we only have 2 clusters, each cluster is described by these 3 keywords. So the first cluster here is mushroom, harvester, fruit. The second cluster is provide arm control. So as you can see, this first cluster mainly ties to interfacing with the actual product that we are trying to harvest. And then the second cluster had all the things related to this technical design of the robot arm. And then here, if you look at the 4th level, like where we condense everything into 4 clusters, we have mushroom, harvester, fruit, provide control video. So this is more controls related functions are clustered in that cluster. There's force, finger position is mainly the end effector control was there, and so on. And then using that condensed knowledge graph, we have our design prompt or system prompt. We tell the LLM that you are a system design synthesis assistant. Use the provided, so we represented that information as in a JSON file. So use the provided JSON file as the authoritative context, saying try to focus on this information only, don't go out and just make up stuff. Generate the responsibilities required for the given design problem and propose design concept alternatives for each function. And this JSON file is the input to the LLM. So let's see what kind of ideas it came up with. So again, as a reminder, on the left, we have knowledge coming from the fruit harvester, and from the right, we have knowledge that is coming from the silicon handling robots. Okay, so here, some of the key things that you will notice if you read all of these carefully is here the focus is more on objects being oriented randomly in 3D space, right? So trying to identify what is the orientation is a very important function as far as the left side is concerned, right? And then the second thing that is concerned is the robot arm should not crush the fruit. It should not damage the fruit, right? So the force that is being applied has to be very tightly controlled. Whereas on the other side, on the right-hand side, it is not too much worried about the orientation, right? The solution does not really have that as a big function. What it is more worried about is damaging the silicon wafer, right? So, and then second thing is it is using controllable adhesion, which is a mechanism with which the robot arm basically picks up the silicon wafer through the adhesion process, which is not something that we see in the fruit examples. Right. In the fruit example, it's always grabbing it in some ways, whereas here it is some sort of a controlled adhesion which can be turned on and off. So you'll see functions along those lines here. So going one step further, we asked the language model to identify all the assumptions that it made while coming up with the solutions. Okay, so in addition to coming up with the solutions, tell us what are the assumptions, what are the hypotheses through which. So here are some examples. It says, adhesion-based gripping approaches are feasible given the presence of adhesion pad and actuating components. So it's thinking that there is some way of using adhesion to pick up the Coke can also. Force feedback is necessary. The robot can mount various handling tools or sensors as needed. And then similarly here, there are similar kinds of assumptions like force control and feedback are available and so on. So this is my last slide. So quick, some conclusions that we draw so far based on what we've done is one is knowledge extraction. So LLMs are very good at extracting information from these documents that are out there, like patents, right? And now this is something that was a very big pain in the past. We could not use that information for doing design, but now with these tools, it is possible to extract knowledge from all of these sources in an automated large scale fashion so that we can actually use that knowledge nicely. Hierarchical knowledge graphs can be used to reduce the context length, which is a big problem in these LLM-based approaches. And then, they're surprisingly good at adapting solutions from one domain to the other domain, which can be leveraged. And then target knowledge extraction helps in broader exploration of the design space, which we saw with personas, and now we're seeing that the same thing with these different kinds of patterns from different fields. And of course, there are a lot of other future extensions that are possible. One is capturing the relationships and constraints between functions, so coming up with the interface diagrams between different components, and then automatic selection of these pattern codes based on a given problem statement. How do you do that is something that needs to be solved. Okay, so that's what I had from the presentation side. I do have one slide which is sort of a summary of the things that came out of the NSF workshop, but I'll let Farooq tell me when or whether to present that or not.
Thank you so much, Dr. Panchal. It was really amazing, especially for me when I am working on LLM-based designing. So thank you so much. It was really interesting to me. And now we open the Q&A session. So please, everyone feel free to open your mic and raise your hand and ask your question.
Actually, I don't have any question regarding the clarification, but just I want to say thank you so much, Dr. Panchal, for sharing this insightful presentation. Actually, I found the concept of using persona to structure reasoning and increase diversity in design outcomes very related to my own dissertation, because as I mentioned earlier, I work on designing a framework for evolving system where different designer or stakeholder persona could similarly represent distinct perspective in decision making. So based on the approach that you have, I started to think how to formalize this diversity between inside my framework. So I would really appreciate if it's possible to share the related paper for me to just go for further information. I could send you an email and ask you for a paper if it's possible.
Definitely, yes. So we have a design science paper that is coming out soon. It's on the first half of the presentation that I did. So it has a lot of details about how we came up with the diversity measure, how what kind of specific things you have to do to make all of these things work. But yeah, send me an email and I'd be happy to share that with you.
Really appreciate. Thank you so much. Thank you.
Thank you.
Thank you, Sarah. Yes, Andrew.
Yeah, thank you, Prof, for the presentation. It was very interesting. I have several questions, but I think I will just ask one because of time, and then we can keep the conversation via email. Yeah, but going through the slides, there was a table you showed on slide 18, where you compared like the different personnel, and I was wondering why the numbers you showed was not diagonal for that case, unlike the previous slide, which had the diagonal. That made sense, that for a mechanical personnel, it should align more with the mechanical knowledge base. But then on that slide 18, I didn't really see that diagonal. So,
right.
Yeah.
That's a great question. Yeah, I think what is going on there is when we generate a set of solutions, those solutions represent some subspace which may not be completely aligned with all the knowledge items in that field. And many times, since there is overlap between the knowledge in different fields, right, that set of solutions that are generated maybe at the intersection or maybe close to the intersection. So it's hard to say, whether it's more closely aligned with one field or another field.
Okay.
And the other thing that we saw is, particularly ME and chemical engineering, right? There is so much overlap because both of them have so much fluids, material science, and energy transfer. Yeah.
Okay, great. Yeah, I will send the mail to ask more questions. Yeah.
Okay.
Thank you.
Yeah. Anytime, please.
Okay, I have a question.
Yeah.
Well, thank you so much again. It was really interesting to me. So one of the challenges that I am facing with extracting the knowledge and put it in a knowledge graph in database is this is very limited, and sometimes I need to remove some of the knowledge which are not still using for our agents and rechange it to another knowledge. So is there any researches that you are working on it to deal with this issue, or any new idea regarding this challenge?
So, can you help me understand, is the challenge with the number of knowledge items that you have, and is the size that is limiting?
Yes, the number of knowledge, and sometimes, for example, in my works, I need to update the knowledge, means that remove some of the knowledge that are not going to be used, and update that knowledge with other knowledge. So this is not a static knowledge graph, it's dynamic kind of.
Yeah. Then in fact, that's a very good question, because there are, when we say the word knowledge, right, it could mean a lot of things. So for example, what we are using here is just functions and components, and we're saying that that is the knowledge that is useful for generating solutions. But then you could think about physics-based knowledge, all the basics of, let's say thermodynamics is knowledge. Then we have knowledge related to all the data tables that are there in handbooks, for example. That's all experience-based knowledge. So figuring out which part of knowledge is important in which context, at which stage in the design process itself is a big open question, right? And I think we can only basically try it out and see which one is better and how to account for this evolving knowledge. I mean, there are different ways of compressing knowledge. Like humans always compress knowledge, right? In many different ways. It's not clear whether that kind of compression is compatible with LLMs, and whether, if we compress the knowledge, it is the same as compressing knowledge in terms of design rules and design guidelines, because that's compression of knowledge, right? So that again is a sort of open question. It's hard to answer.
Thank you so much, Dr. Panchal.
Thank you.
So any other questions?
Yeah, just a quick question. Yeah, thank you so much, Dr. Panchal, for the talk. And my question is that you mentioned that hierarchical knowledge graphs help reduce the like the length of the context. So could you explain how that affects the LLM's ability to reason across the complex design problems?
Right. So the idea is that, if I have, let's say, 5,000 nodes in my graph, I cannot give the 5,000 nodes. In fact, we tried that. We took all of those things and just dumped it. Clearly, it will forget everything. It will only take the last whatever X number of words. So then we said, okay, we need to reduce the number to maybe 500. How do you do that? The idea is, when you do hierarchical clustering, right, it will come up with these clusters saying, okay, one cluster is representing one types of things, right? So if they are finger-based, for example, grippers, then it will put all of them in the same bucket. Whereas if there are these other types of, grippers, then it will put it in a different bucket. Right. And then what if we just gave it all of those things? Okay, you could use finger-based things, or you could use these other types, or you could do this. So that basically condenses information into a smaller number of words.
Yeah, thank you.
Thank you, Doug. Now I want to introduce Dr. Naidu.
Okay.
Hi.
Hello, nice to see you.
Dr. Panchal, very glad to see you again. I worked with Professor Mistry and Janet from last about 5-6 years. My area of expertise and interest is design for patentability, which is a very perfect alignment with what you are telling. So I was wondering, because we always grapple with the issue of two particular notions called, one is obviousness and one is anticipation. So normally the examiner, the 3 or 4 patents which I have worked with US patent examiners and got it to successful grant. Generally it is a dilemma that, what the examiner will come out with the prior art search, what they will allege to be obvious in view of the prior art, and what they will allege against anticipation. So there are specific sections, as you may know. 112A is one section which is a very favorite for examiners. So I see one application here of this work, one part of it, a potential application is, if the LLM and your approach can predict reasonably the anticipation and obviousness allegation, it will actually help in developing a patent, developing a concept and developing a product which has a better chance of patentability going down the line. After 2-3 years only we come to know. And that is too late because we can't add any new matter in an application because the priority date, everything changes, right? So it will be very helpful if we can predict, because you have everything in place. You have a large model, you have so many patents, up to 100 patents you told in the area. So if we can predict, and then there can be a design fine-tuning done to overcome those objections by the examiner. So it will improve, even if 10% the possibility of patentability improves, it is a great benefit for the innovators. because there's a lot of money spent, and then they come to know that, okay, it's obvious in view of the prior art. Yeah, thank you.
That's very interesting thought. Yes, I was wondering whether, so we have information about all the awarded patents. Do you know whether there is information about patents that are not awarded and the reasons are like, is that something that is documented somewhere? Because I'm
Yeah.
sure if we can use that, like those examples, then
Yeah.
possibly these LLMs will be able to identify those kind of flaws in a given application.
Yeah, that's exactly where we can collaborate potentially.
Okay, yeah.
Because I know where those information, they're a little bit hidden. There's something called private pair, which used to be there, where you have to log in as a user of, I am a registered customer of USPTO. So I have access to private pair, but there are ways to know the prosecution history.
Oh, okay.
So every patent which has been granted and every patent which was rejected, their reasons for rejection is available, which is sort of, it is available, like it's not open, but it's possible to get access to that. And it's not any confidential document, like you can always get it, even formally you can get. And if you are a US patent registered customer, you can access the entire database.
I see.
So I think that will be a very good and very interesting and very useful application to see the prosecution history of those patents which are not only granted, but even those who have not been granted or rejected.
Right. Yeah.
And then a new design or a concept, a variant can be fine-tuned, which has higher probability of success down the line.
Right. I think this is great. Yeah, we should discuss more about this.
Yeah, sure. Thank you very much, Dr. Panchal.
Thank you.
Thank you so much, Dr. Naidu. Very interesting topic you posed. And any other comments? Shehusani, Percy, Behram Shah, Janet, Ola, Farokh.
How close is what you have gotten to someone using TRIZ?
Yes, I think, so TRIZ, I think, tries to do that manually.
Yes, I know. I was wondering.
So my guess is that, we can basically come up with new types of concepts like TRIZ by using this kind of methodology. So TRIZ is very specific to certain types of solutions and so on. But because I know now people have been using LLMs for requirements generation, a lot in the software engineering domain. So if we can look at the entire design process and at each step, if we can identify what are the different ways in which we can use LLMs, I think there would be some interesting.
Okay. Thank you.
Thank you. Yeah.
Thank you, Janet. Farokh, closing remarks.
I'd like Shehu to talk about how this would be relevant to his supply network deal and how he could use that in the Nigerian military for the supplies. Shehu?
Hello, Farouk. Thank you. Thank you very much for the presentation. Actually, I'm working on the digital twins for the supply chain now because we have the issues of downtime. So we are looking at preventive maintenance and looking at predictive models. So this came very timely because we are looking at what we're trying to avoid is, yes, sometimes we use the LLMs, but trying to avoid some kind of bias, because once you are using the LLM, sometimes it's biased towards your own thoughts. So we try as much as possible to try to eliminate some of this bias, but sometimes because we're not actually using it fully for methodology, because if you're going to use it for your methodology, then it's going to be, there's going to be a lot of bias towards the outcome of your results. So it's really timely, and I'm looking at the first aspect of looking at like a cognitive thinking, bringing a lot of ideas together and trying so that you can have a methodology you're trying to use. So I'm trying to really look at this aspect and trying to incorporate it in what I'm working on now, the digital twins of some of the supply chain which I'm working on now, which has to do with a lot of preventive maintenance, and it has to do with reducing the downtime of some of the maintenance of some of the military aircraft that we have. So it's really timely, and thank you very much for this presentation. Thank you, Farouk.
Sounds great. Thank you so much. Yeah, I think this kind of an approach used with maybe product manuals or some other sort of documentation for maintenance history may be very useful. I have one student, a master's student, who is exploring how we can use this kind of an approach to do design for manufacturability, because now we can represent geometry in the form of Python code, and then if we can use guidelines for design for manufacturability, can we generate a new geometry which is actually adapted to those rules, is one approach.
Percy, he's in Houston. Any comments? Percy? Damodar, comments? Right. Jitesh, this was absolutely phenomenal. I have received a couple of requests for your papers.
Sure.
And so if you could email them to me, I'll circulate them to the people who have contacted me.
Definitely, yes. Thank you.
I've also received a request for you to be on a master's thesis committee, and we'll get in touch with you.
No problem. I'd love to.
All right. So I'm going to stop recording in our usual way. We will we'll just chit chat